Welcome to the UG students. Now we are going to the JAM question solution 2024. The first question for the JAM question solution is the peptide synthesis. In the peptide synthesis, the peptide bond is formed by the reaction of the carboxylic acid with the amine groups. And this is the amide bond, and different type of the amino acids are condensed together to form the peptide. It may be dipeptide, tripeptide and polypeptide. It has two bonds. One is the N-terminus part, another is the C-terminus. And here the examples where the artificial sweetener is the dipeptide, and which under cleavage of the amide bond to produces the aspartic acid and the phenyl line. So the option of the artificial sweetener is the B, is the correct option. And the peptide molecules can be identified by the admin degradation, where the 40 amino acid residue can be determined in the admin degradation, where the phenyl thiocyanide used as the reagent for the determination of the peptide sequence in the admin degradation method. This is the problem for the reagent chemistry, where the ketomethyl group is converted to that of the carboxyl group. In the option A, the metachloroperbendic acid is used for the Baeyer-Blazer oxidation reaction. The in nucleophilic addition, it produces the negative charge on the oxygen atom, which undergoes alkyl migration to that of the oxygen atom, produces the ester derivatives, and which ester derivatives under hydrolysis in presence of the NOH and aqueous HCl produces the hydroxy compound, and this is matched with the given problem, not matched with the given problem. So the option A is wrong. And in the option B, the osmium tetroxide is used for the cis hydroxylation of the alkene. Here the substrate has no alkene part, so the cis hydroxylation is not take place. So the second option is also wrong. In the third option, the ketomethyl group is present. We know that the ketomethyl compound undergoes halogenation in presence of the enolate intermediate, and trihalogenated derivative is formed, which undergoes hydrolysis to form the carboxylic acid derivative. Here the sequence of the reaction where the carboxylic acid is formed by the intermediate of the trihalogenated derivatives, and RDO form is formed. And the DMDO is used for the epoxidation of the carbonyl compound. Here the epoxidation is not the product, so the option D is also wrong. In the substitution reaction, the potassium cyanide react with that of the 3 degree halides to produces the cyano substituted derivatives. The mechanism for that, at first the CBr bond is cleaved to produces the carbonyl carbocation, and then this carbocation undergoes resonance, and it can be stabilized by the phenyl ring resonance or the hyperconjugation effect, and produces the stable carbocation, and which undergoes nucleophilic addition to produces the desired product. So the carbocation is the intermediate, so the reaction is SN1 type. We know that the rate of the SN1 reaction is depend only on the concentration of the substrate, but not the concentration of the nucleophile. In the problem is that if the concentration of potassium cyanide is increased 4 times, that is the concentration of the nucleophile. Since the rate is not depends on the concentration of the nucleophile, so the rate is unaffected in presence of the increase of the potassium cyanide concentration. So the option A is correct. Now this is the rate of the solvolosis reaction of the different substrate, where the different type of the halide undergoes reaction in presence of the nucleophile. The rate is highest for the perennial halide, where the carbocation becomes stabilized as a 3 degree carbocation, and it has been observed that the phenyl substituted derivative has lower rate compared to that of the perennial halide. This is the problem for the pericyclic reaction. In the pericyclic reaction, the substrate is the 3,3 sigma-tropic shift. That is, if we naming the substrate as 1, 2 and 3, and this becomes 1, 2 and 3, we know that in the 3,3 sigma-tropic shift, 3,3 bond is formed and 1, 1 bond is cleaved. and this contain at a particular conformation, that is the both type conformation, and produces the intermediate this compound, and after that the methyl group is in the syn orientation, so the option A is correct. Similarly, this type of the reaction is also happened in the 3,3 sigma-atomic ship rearrangement, where the oxygen nucleophile can add it to the aldehyde and produces the 3,3 sigma-atomic rearrangement pieces, and this 3,3 sigma-atomic rearrangement produces the desired product. Similarly, the 3,3 sigma-atomic shift is also happened in case of this active ferromen, where active ferromen is converted to the inactive ferromen via 3,3 sigma-atomic shift rearrangement. This is the problem for the heterocyclic chemistry. In the heterocyclic chemistry, the acetic anhydride reacts with the pyridine oxide to form a O-acyl derivative, and then this O-acyl derivative undergoes nucleophilic addition and the cleavage of the OAC bond to produces the derivative, heterocyclic pyridine derivatives, and the option D is the correct. Similarly, the PCl3 is also react with that of the nicotinic acid derivatives, to produces the chloro derivative, that is the chloro substituted pyridine derivative has also formed by maintaining the similar type of mechanism. We know that the intramolecular aldol condensation reaction, in the intramolecular aldol condensation reaction, the precursor has been formed by the cleavage of the alkene molecules to produces the dialdehyde derivatives, and then this dialdehyde derivative has proper position for the intramolecular aldol condensation reaction to produces the cyclopentene derivative, so the option B is correct. Similarly, the similar type of the chain type of derivative also is the precursor for the intramolecular aldol condensation reaction, but the proper ring should be maintained, that is the carbanion is formed in the terminal side and produces the 6-member ring derivative, and then this 6-member ring under elimination of the water produces the 6-member compound. Here the 4-member ring is not possible due to the angle strain. This is the problem from the neighboring group participation reaction. In the neighboring group participation, the two eliminating group must be present to that of the anti-periplanar orientation. Here, it converted to that of the chair conformation, and the acidoxy group is added to the opposite side to that of the leaving group and produces the desired product. And if we see that the 1:1 enantiomer mixture of diacetate derivative has been formed, so the option is the B option is the correct. A racemic mixture of trans 1,2-diacetyloxy cyclohexane has been formed. And similarly, this is the example, and here the two compound A and B produces the same mixture of compound after the neighboring group participation reaction. This is the example for the semi-quinacol rearrangement. Here the amine and the hydroxyl group in presence of the nitric acid produces the semi-quinacol rearrangement precursor. Here the nitric acid gives that of the nitrogen elimination, and then the hydroxyl group is added to that of the anti to that of the nitrogen and produces the epoxide. Here the fitting inversion is not take place due to that of the trans-decalin has been locked at the trans position, so since it is locked, so the fitting inversion is not possible. Here the hydroamine group is after nitric acid reaction, it produces the nitrogen gas, and then the methyl group is migrated anti to the nitrogen and produces the carbocation intermediate, and then this carbocation undergoes the resonance to produces the carbonyl compound. Similarly, the semi-quinacol rearrangement is also used for the ring expansion reaction, where the cyclohexane derivative is converted to the cycloheptanone derivative. These are the some examples where the semi-quinacol rearrangement takes place and produces the cyclopentane aldehyde derivative or the cyclohexanone derivative or the epoxide compound according to their conformation. This is the examples for the Ohm-Palm reactions. In the Ohm-Palm reaction, the secondary butyl lithium produces the carbanion, and then this carbanion undergoes SN2 reaction, and the cleavage of this protected form to produces the carbonyl derivative, and this carbonyl get further protection in presence of methanol BF3 etherate to produces the protected form. And these examples have been taken from the Claydon groups, where the bicyclic compound can also synthesized using the Ohm-Palm reaction from the precursor of the meta-dihalide derivative with the dibromide derivatives. This is the problem from that of the aromaticity. In the first compound, the compound after the release of the proton, that is the acidity, means the release of the proton of the H plus ions produces the carbanion, and this carbanion is the 3-member carbanion, and it contains the 4 pi electrons, so it becomes anti-aromatic. And the 2 compound after release of the proton becomes aromatic, and 3 compound after release of the proton it produces the carbanion derivative. The negative charge on the carbanion derivative, that is this is the sp2 hybridized, so the negative charge is more stable. And in case of the 4, after negative charge formation, it becomes anti-aromatic. So the compound 1 and 4 is the anti-aromatic, so it is highly unstable. That is 1 and 4, it becomes less acidic and it has higher pK value, and the compound 2 has higher acidity, means it becomes stabilized by the deprotonation. So the compound option B is the correct, that is the 2 is more acidic, then it becomes 4, and then it becomes 3, then it becomes 1. And so the 1 is less acidic due to that of the it gain anti-aromaticity after the deprotonation. These are the some examples where the different type of the aniline produces the different aromatic compound. That is 2 anilines, it is the anti-aromatic, 6 aniline is aromatic, and 8 aniline is non-aromatic, 10 aniline is non-aromatic, 12 aniline is anti-aromatic, and 14 aniline is aromatic, and 18 aniline is also aromatic compounds. Thank you for the watching of this